Hello, and welcome to the Maths Diagnostic Question of the Week number 22 with me, Craig Barton, where each week I select a question that has been uploaded to my Diagnostic Questions website and we look closely at it to see the number of students that went for each response, but far more importantly than that, we look in depth at the explanation students gave for each of their responses as a means to identify the crucial mistakes and misconceptions they may be holding. Now, I'm currently working my way through revision with my adorable Year 11 class, and it's come to light that a few of them have issues with tree diagrams. And it really got me thinking about the whole concept of tree diagrams. And the more you think about it, the trickier they get. So I thought, what better subject to do for our diagnostic question of the week this week than tree diagrams themselves? So let's find ourselves a good question on it. So I'm going to go to data and questions, and I'm going to have a little scroll down and I am going to search by most answered, and as I've been doing the last few weeks, I think that's a really nice way to get some decent data size. I'm then going to go for a bit of mathematics, and then I'm going to have a look in data and statistics, and let's see if we can find ourselves a nice one. And the one I've got in mind is this little beauty here, so let's call that up and have a look at it. Now, it's this point at this point of the video where I recommend you give it a little pause, have a look at the question itself, and ask you the following questions. Firstly, which is the right answer? Secondly, which do you reckon the most popular incorrect answer is given by students? And thirdly, what explanations do students give for that wrong answer? So pause the video and then restart it whenever you're ready. Okay, welcome back. Now, if my mathematics is right, and often it isn't, I reckon the correct answer is A, 0.84%. But I wonder how many students gave that answer, and I wonder how many students gave each of the wrong answers. Well, let's have a look, and let's go to advanced, and we can see this question's been answered 434 times, and if we just flick to percentage mode, we can see that only about half the time are students getting it right, and B and C are by far the most popular incorrect answers. Now, firstly, let's have a look at the ways students explain the right answer, and then let's really delve into these B and C and also D options. So, firstly, how are students who are getting it right explaining it? Well, I'll tell you what, there's some absolutely wonderful explanations here. These could come out of the textbook, but they're even better because these have been written by real-life students. So you get some beautiful explanations here. I like this one, nice and concise. I could win the first and second. That's 0.6 times 0.6. I could win the first and lose the second. I could lose the first and win the second. Beautifully explained, really nice. And then we get the same thing but in a bit more detail, really breaking it down, and so on and so on. I also like this one that talks about branches. Going along the first branch, there are two possible scenarios of winning at least once, and then on the bottom branch you can win once by going 0.6 times 0.4. Really nicely explained. Now that's the way I would do it, and that's why I'd expect most of my Year 11s to do it. But it really came to light when I was discussing tree diagrams with them that there is a major misconception going on. And as I say, when I started thinking about tree diagrams themselves, I realised that there's two separate skills involved with tree diagrams. Firstly, there's the whole mathematical operation. In this case, it might be multiplying decimals and then adding them, or in other tree diagrams, it might be multiplying fractions together and then adding them. But on top of that, there's the one that can often be kind of put to one side, and that's understanding what tree diagrams are themselves. And as I say, the more you think about it, the trickier they get. Because in a sense, when you look at this question, you're asking students to kind of picture four different alternative realities. The first of which is where the person wins the first game and then wins the second game. But then we ask them to shift their attention to a parallel universe where actually what happened is they won the first game and then lost the second game. And I get many students saying to me, well, what actually happened here, sir? What happened in that first game? And you've got to say to them, well, we don't know, but let's pretend they won the first and won the second. What would be the probability of that? And so on. And the more you try and explain it, the more tricky and confusing it gets. And that's why I like this question, because it isolates the actual skill of understanding tree diagrams as opposed to focusing on the decimal operations. So let's have a look at this. Why are students going for B 0.24? Well, you can probably have a guess here. The probability of winning at least one game, well, the probability of winning one game is 0.24 because it's 0.6 times 0.4. Is that what students are doing? Well, let's have a look. Let's flick this to B and see what they're saying. And indeed, it seems to be that they are, but there's a bit more than that. So this student here says, I think this is the answer. You do 0.6 times 0.4 to get 0.24. So I think that student there has the misconception that they think winning at least one game is the same as just winning one game. And there's only one way to do that. And look at that one there. follow the path of the win then loss. But then this is where it gets interesting, and then divide them. And this comes here as well. It could be the win and the loss, which will be 0.4 times 0.6, and the loss and the win, which would be 0.6 times 0.4, both of which will be 0.24. So no need to add them there in the student size. They're both 0.24, so there's the answer. This is a similar one here, or they're written in a slightly confusing way here, but that also explains that they just leave the answer at 0.24, no need to add them together. So students who are going for 0.24 are displaying two different things. Some of them believe that you just travel down one branch and there's only one way to win at least once. But more interestingly than that, some students have noticed that there's two ways to win exactly once. But as both those probabilities are the same at 0.24, they're leaving it at that. So the answer is 0.24. And that's a misconception I never encountered before. But the more you think about it, that is something quite logical that a student could think. And what about C, 0.48? Well, again, this is probably a little bit more common, and indeed over 1 in 5 students selected this answer who answered this question. You can probably predict where this has come from, 0.48. And this is a misconception with the concept of the question itself, the probability that I win at least one game. I think students here are seeing that as what is the probability I win exactly one game. Win and a lose, lose and a win, add them together. But don't take my word for it, let's read what the students have said themselves. So here we go. We've got here, let's have a look at this, is a good one here. If he loses the first and wins the second, that's 0.4 times 0.6, 0.24. If he wins the first and wins the second, 0.6 times 0.4. Add them together, 0.48. And all the answers down here are suggesting the same thing. Take the 0.6, multiply by 0.4, multiply that by 2. And so on. And this student even refers to the probability of winning at least once, and yet they've clearly demonstrated that they've worked out the probability of winning exactly once. So a common misconception. And then what about this for 0.3? I didn't write this question, so I thought, where on earth does 0.3 come from? But I'll tell you what, it's caught a couple of students out, and they've given some absolutely fascinating reasons for it. Two in particular. So just have a look at this. I like this one here. Because 0.6 divided by 2 games equals 0.3. So they've seen the probability of winning is 0.6. You want, there's 2 of them going on. You want to win at least one, so divide 0.6 by 2 and you get 0.3. Fascinating. And then another student believes that to get the probability, you just add everything together, and therefore they've got 0.3 coming out of that. Really interesting stuff there for how students get it. So what on earth can we do with all this? Well, hopefully the students can resolve their own misconceptions, because if they get something wrong and then they click the review button and start reading through some of these explanations for the correct answer, I mean, how could you fail not to understand this from some of these beautifully explained reasons? And there's pages and pages of these, and all it takes is for one explanation to hit home with the students, and hopefully that's their misconception resolved. But it's really made me think about my own teaching and the fact that I've got to spend a bit more time on the actual concept of the tree diagram itself before I just start ploughing in and saying you just do this times this and then add them together to get your answers. All right, I will. Oh, and I should say as well, sorry, before I shoot off, that there is a quiz on tree diagrams, and if you just go to the question page itself, just click the image, you'll see here related quizzes, and if you give that a click, you'll find that there's one there, tree diagram collection, which is 10 questions on tree diagrams, which is hopefully very useful. And I'll be back with a fresh question of the week next week. Take care and bye for now.